accueillir ici au séminaire à Montréal de Staffan LARSSON de l'Université Göteborg de la Suède. Stéphane est professeur de linguistique computationnelle au département de philosophie linguistique et théorie des sciences de l'Université de Göteborg. Il est également membre du CLASP, le Centre de recherche pour la théorie linguistique et les études de probabilité, et il est aussi cofondateur et directeur scientifique de Talkomatic, qui conçoit des systèmes de contacts vocaux spatiaux robustes. Ces domaines d'intérêt sont larges. Ils comprennent les systèmes de dialogue, le langage, la perception, la pragmatique, la sémantique formelle, la coordination sémantique et la philosophie du langage. Bref, c'est toute la gamme de sciences cognitives. Son thème est la signification et les classificateurs coordonnés et composés. Just a few words in English. You've already seen the abstract and the bio, so I'll just quickly say that Professor Larsson is Professor of Computational Linguistics in the Department of Philosophy, Linguistics, and Theory of Science at the University of Gothenburg in Sweden, a member of CLASP, the Center for Research on Linguistic Theory and Studies in Probability, and co-founder and chief science officer of Talkomatic, about which he may or may not talk today. His areas of interest include dialogue, language and perception, pragmatics, formal semantics, semantic coordination, and philosophy of language, the full spectrum of cognitive sciences, and his presentation is Meaning as Coordinated and Composable Classifiers. Professor Larsson.
Thank you very much, and thank you very much for inviting me to the seminar. It's an honor. I've been following some of the previous seminars, and so I'm going to be talking about some like similar themes, of course, but from I think a slightly different angle than most of the other talks, so from the angle of formal semantics. I have a lot of slides here, and I'm going to skip over them, some of them a bit quickly, but I want to keep them in the presentation for purposes of like answering questions and if somebody wants to go deeper into things. And another thing is that there is some technical stuff in here. I will try to explain it in ways that can, because I understand it's an interdisciplinary seminar and not, everyone is deep into linguistic formalisms. I hope I can explain things, but feel free to ask if there's something that's, that you need to know more about. So I'm going to talk about first some introduction, and then this formal framework that I'm working in, TTR. And then I will be talking about these three themes, the classification, coordination, and compositionality. So first of all, the questions that I'm interested in here is that how is linguistic meaning related to perception? And also, how do we learn and agree on the meanings of the words that we use? And to explore these questions, we're developing, I'm going to be talking about work here that I've done together with other people to a large extent. We're developing a formal judgment-based semantics, where notions such as perception and classification, judgment, learning, and dialogue coordination play a central role. And a lot of this, the origins of this work is from Robin Cooper, who you can see down there to the left. And also some of this foundational work has been together with Professor Simon Dobnik. So a key idea is to model meanings, perceptual meanings, as classifiers of real valued perceptual data, and to train these classifiers in interaction with the world and other agents. So one starting point here, or useful terminology, is Marconi, 1997, distinguishes inferential and referential meaning. So inferential meaning is what enables you to infer stuff from uses of a word, sort of high level or symbolic, and the stuff that you would typically model in formal semantics. So if you learn that someone is a bachelor, you will know that it's an unmarried man, for example, unless it's the Pope. Then referential meaning allows speakers to identify objects and situations referred to by words, and that's sort of modeled as a low level or sub-symbolic on that level. And the hypothesis is that referential meaning can be modeled using classifiers whose output is formal representation. So it's bridging that gap. So, okay, what is classification? We have two agents here looking at a color blob, and they classify it as being a blue blob, and they name it like that. But of course, we can classify things differently. One of the agents might think it's purple. And then if they want to be able to distinguish different colors for some purpose, they need to resolve this disagreement and coordinate. So they can talk to each other to resolve it and come to an agreement where they decide to call it blue or maybe to call it purple. So this classification can be coordinated. They might also actually end up calling it something else. Maybe they need a new word for this blue-purple thing. So coordination can also be creative and go beyond what any of the agents had at the outset. So the fundamental idea here is that agents associate linguistic expressions with structured information. And by interacting and updating these structured information that is associated with expressions, these agents coordinate on meanings. So interaction in a shared perceptual environment we take to be essential to symbol grounding. And to the extent that they are sufficiently coordinated with respect to the task at hand, then these expressions have meaning. This is usually where I stop in my attempt to define meaning. I don't actually say what meaning is, but I try to say when there is meaning. So it's meaning when people are sufficiently coordinated with respect to task at hand. Yeah. So, and then how does that happen? Well, there is a multitude of procedures in natural language to enable this coordination. Some of it is overt and some of it is more hidden and going on sort of behind the scenes. And also the meanings of complex expressions such as a sentence is derived from the meanings of the constituents. So this is the compositionality. And this crucially then includes the perceptual meanings modeled as classifiers. So basically the problem that occurs here is like, how do you do compositionality for classifiers? So our task here is to provide a formal semantics and pragmatics that accounts for all of these things. But we also want to keep around, because formal semantics has been around for about 50 years. It's been an accumulation of insights and knowledge about natural language meaning, and we don't want to throw that out. But we also want to connect to recent work on machine learning for perceptual classification. So that has been a big topic in machine learning, like how to classify images and so on, and how to like put descriptions, automatically describe what's in the picture and so on. So we want to connect to that. So what is formal semantics? Because I'm not assuming that the whole audience is familiar with that. It's the study of meaning in natural languages using formal tools from logic and computer science, and often with the hope of implementing something in a computer that can actually be useful. So in formal semantics, there is a sort of received view, like the majority of papers being published takes this possible world semantics approach. Based on tradition from Richard Montague in early 70s, who was the first to try to apply these formal methods to natural language in a sort of systematic way. And one crucial thing in that kind of theory is that meanings of words such as dog is taken to be the extension of that expression. So the set of all dogs in the world. So this double bracket is often used for meaning. So the meaning of dog is going to be a set consisting of all the dogs in the world. That's actually a fairly extreme view on meaning, because you're sort of saying that that's all there is. There are just dogs. There is no idea of the dog. So as a research program, possible world semantics has in many ways been quite successful. Yeah.
Staffan, we have one, maybe it's premature, but we have one question concerning results showing that the subdivision of categories, boundaries that define the extent of meaning based on coordination via communication is suboptimal. How do you reconcile with the function driven by referential semantics?
I think we maybe better return to that question at the end. I think it would be easier.
The person who asked it, Mao, agrees that it's premature, and I probably shouldn't have mentioned it.
Yeah, but it's yeah, okay. I'm not exactly sure I understood the whole question, but maybe let's return to that a bit later.
Okay.
Thank you. So yeah, so I mean, this kind of semantics has been successful in accounting for several things like compositionality, quantification, modality, logical inference, and so on. On the other hand, it's been less successful in accounting for some other things like the relation between language and perception, semantic learning, vagueness. And in a paper from last year, I argued that actually this idea that natural language words or expressions have determinate extensions is actually not very feasible. But I'm not going to go into that today. But so what we actually want to model is intentional meaning. So the intentional definition of word gives the meaning by specifying conditions when it can be used. So, or the general conditions which an object must fulfill in order to be denoted by a word. That's Carnap's definition. And this possible world semantics doesn't really do that. It doesn't represent intentional meaning independently of extensions. Okay, so we opt for another approach, this type theory with records, but that still keeps around many of the insights from the possible world semantics. So TTR starts from the idea that information and meaning is founded on our ability to perceive and classify the world. So it's based on this notion of judgments, of entities and situations being of certain types. So now I'm going to go a little bit into technical stuff. If you really don't like that kind of stuff, you can, I hope you will, I'm pretty sure you will be able to follow anyway, but maybe there are some people who are interested in this kind of thing. It's just a few slides of technical stuff. But so the very foundational thing is a judgment that something is of a type. So just write like A is of type T. So that's a judgment. So what are these types? Well, one is type in TTR is the type of individuals, and another is real, the type of real numbers, and so on. And there are many other basic types. But then there are also complex types. So if you have T1 and T2 be of types, then being types, then T1 arrow T2 is a functional type whose domains is objects of type T1 and whose range is objects of type T2. Now this looks maybe a bit challenging, but it's actually not that challenging, I hope. So TTR has records and record types. So this is a record here. It has labels and it has values. And then this record is of this type, and you have the same labels here. If this object here is of this type, this object is of this type, and so on. And the only, right, you can see that these things are referring back to these labels. Why is that? That's because we have dependent types. So that's most easily explained by an example. So here's a record where we have a referent, ref, which is an object. We have let's call it a constraint. Two constraints here. They are some kind of thing. Let's not say much about that yet. So this kind of record is of this type, provided that this object 1, 2, 3 is of type int. This S4, 5, 6 is of type man ref, but crucially this ref here is referring to this label. So this object is of this type, but this type actually involves this object here by referring. Okay, it's not as complicated as it might sound. So, and another technical notion is that of a p-type. It's like a proposition, like the content of an assertion. So you can construct types from predicates. So actually, this is a type. So predicates like run or man. And yeah, it's corresponding roughly to propositions of first order logic. And the fundamental type theoretical intuition is that something of a p-type, p, so that's a predicate, and then some arguments, is whatever counts as a proof of that p-type. So here you can say that S456 is a proof that this object 1, 2, 3 is a man. And S789 is a proof that that referent is running, that the object 1, 2, 3 is running. So now we're just using this S thing here. We're not saying anything what is a proof. Actually, we'll see later how low-level perceptual input, like information derived from perceptual organs or technologies, can be proofs that were included in proofs. Okay. Okay, final technical thing. You can put types together. You can merge them. It's basically like conjunction. So if you have T1 and T2 be types, then T1 meet T2 is the me type. And something is of the me type if it's both of T1 and T2. And then you can also put them together, having this merge operator. So it's, if you have this record type here and this record type here, you can merge them together into this. If they share a label, you will put a conjunction here on the type level. Okay, we're going to be making use of this later. If you didn't follow that exactly, don't worry. It will be possible to follow the rest anyway. Okay, now let's talk about classification and symbol grounding. So obviously, this is not new to any follower of this seminar. So part of learning a language is learning to identify individuals and situations that are in the extension of the phrases and sentences of the language. That's one way of putting it. So for many concrete expressions, this identification relies crucially on the ability to perceive the world and to use the perceptual information derived from the world to classify individuals and situations as falling under a given linguistic description, that is, being part of the extension of that description or not. And this is, of course, the view put forward by Staffan in 1990 to address the symbol grounding problem. And that for a long time I knew about this paper and I had read about it. And when I finally got to read it, I was surprised to see that there wasn't just the problem, it was also a solution, right? At least the start of a solution. And that I thought was also a very good solution. So what do you need? You need a hybrid system encompassing both symbolic and non-symbolic representations. So now, obviously, I run the risk of misrepresenting an author in plain view, but I'm going to take that risk. And the latter representation such that they can pick out the objects to which they refer via connectionist networks that extract the invariant features of their analog sensory projections. And also learning non-symbolic representations, so a connectionist network that learns to identify icons correctly from the sample of confusable alternatives it has encountered by dynamically adjusting the weights of the features. And finally, compositionality, where complex constructions will all inherit intrinsic grounding of the grounded set of elementary symbols. So basically, these are the ideas that we follow and specify further and try to formalize. I mean, this specifically mentions connectionist network, which was, of course, what people were doing then, and actually what people are doing now again. But there are also other kinds of classifiers around. So what is perceptual meaning? We mean that aspect of meaning of some linguistic expressions, maybe not all expressions have them, but for example, concrete nouns or noun phrases referring to physical objects do have perceptual meanings. And it's that aspect of the meaning which allows an agent to identify perceived objects and situations as falling under the meaning of the expressions or not. So that's one aspect of the referential meaning. And we want to integrate perceptual meaning and low-level perceptual data into formal semantics.
Staffan,
So
we have one question.
Yep.
Yeah, one question I think you will accept. By
Yep.
compositionality, do you mean the same thing that Jerry Fodor means? And could you just say in one words what you mean by compositionality?
Okay, so the compositionality principle is that the meaning of a complex expression is a function of the meanings of the parts and the way they're put together. That's what I mean. So like how, if you know the meanings of the words in a sentence, how do you figure out the meaning of the whole sentence?
Okay, thank you.
So, yeah. I think that's what folder means as well, but I'm actually not sure about that. Wait, yes. Yeah, so we want to mix this high level and low level stuff to have such a hybrid system as proposed. So to enable learning and coordination of perceptual meaning, then we need a framework where intentions are represented independently of extensions, and that are structure objects that can be modified, and that also include classifiers of perceptual data. That's the only way I can see that you can actually combine all these desiderata. And as I mentioned before, possible world semantics doesn't really represent intentions independently of extensions, so it makes it not very useful. So classifiers are functions whose domain is typically numerical, so like real valued or integer binary vectors, for example, that, or like, you know, a digital image is just, you know, it's numbers, digital. So, and whose range is a set of categories, or maybe a probability distribution over categories. And we will regard classifiers as at least part of representations of agents' takes on intentions of linguistic expressions. Classifiers, as intentions, produce judgments whether some perceived thing or situation falls within the extension of a linguistic expression. This slide is just to point out that we know about related work. And since I have a bit too many slides, I'm going to skip over it. There's lots of related work, but not doing exactly what we're trying to do here. And I'm happy to return to that if somebody wants me to. So let's go into an illustration. So we want to use this as a very base. I want to have like an example, a running example of perceptual classification. So suppose we have a square surface and you have objects being placed on the surface. And to classify an object, so then the task is to classify objects as being to the right or to the left. So to do that, we imagine maybe a robot directing a sensor like a camera towards the surface, getting a sense reading, a picture from the camera, applying some kind of transformation, returning a position of the object that you're looking at. So that's again actually just a two-place vector. So that's like a higher refined version of what you're perceiving. You're now identified an object and you know its position. And then you apply, in this case, a perceptron classifier, super simple classifier, to that coordinate vector and returning 1 or 0 depending on whether this object is deemed to be to the right or not. And here this is the perceptron's idea of what's to the right or left, this line. So anything to the right of that gives you 1 as output. Yeah, so the perceptron is here used as an example of a classifier, but this account is general and you can basically use any kind of classifier. Classification of perceptual input can be regarded as a mapping of sensor readings to types, so the categories or types. And the perceptron, of course, is a very simple neuron-like object that takes a couple of inputs and gives you 1 output, and you have a weight vector and an input vector, and if you multiply those and they exceed a threshold, then you get 1 out. So this is a very, as I said, simple classifier. It's limited to learning problems which are linearly separable, and we will at least now assume that the distinction between left and right is linearly separable. Okay, how do we put these now into formal semantics? And we're going to add a little bit to this example setting, put it into a game. So this simple game is intended to capture some of the properties of first language acquisition. So you have 2 agents A and B. Facing a frame surface, A has a bag of objects that you can attach to the frame surface. So a round of the game is played as follows. A places an object in the frame. B looks at this object, perceives it, and form some idea of this perceived situation. A says left or right, or more verbosely, this one is to the left, this one is to the right. B then interprets A's utterance based on, with respect to the situation, or B's take on the situation, yielding a p-type. So when A says this one's to the left, he's referring to that object that you just put up on the surface. And then B judges whether, according to B's take on the situation, is of that type, so that, you know, is it actually to the right according to what the way B sees it. If it's not, then B here, being sort of the student, assumes that A, the teacher, is right and defers and says, aha, oh, it was to the right, I didn't realize, and then learns from that. Otherwise, B says okay, and they proceed. Okay. Super simple, but enough to illustrate some basic points. So in first language acquisition, training of perceptual meaning typically takes place in the situation where you have a shared focus of attention. So we're going to limit the analysis to that kind of case for now. And we assume that the dialogue participants are able to establish a shared focus of attention. So this is something that infants can do quite early on. We assume that some simple sensor collects sensor input from the environment, getting a real valued vector, and we assume that this sensor is in fact oriented towards the object in the shared focus of attention. And we represent this then as a record. So here's our situation represented as a sensor reading, this position vector, and this focused object, object 45 in this case. Okay. So this position sensor just returns the two-dimensional vector representing the position. So in S1, B sensor is oriented towards an object 45, and this SR position sensor returns a vector corresponding to the position of object 45. Now we can formulate a classifier as a function with a TTR type. And in fact, instead of a Boolean output like 1 or 0, we're going to have a p-type as an output saying whether the object is to the right or to the left. So we have a function that takes a weight vector and the threshold. Those are the parameters of the classifier. It takes a situation where you have a focused object and a sensor reading, and it gives you back a type. So if you have the parameters of this type and you have some record of this type reflecting the situation you're in, then this classifier, taking those as arguments, is going to tell you that this object, which is the value of this field in this record R, is to the right if the sensor reading multiplied by the weight vector exceeds the threshold. That's the typical perceptron condition. Otherwise, it's to the left. So this function here is defined outside TTR. In fact, that could be an arbitrarily complex computer program or deep neural network or whatever you want. Here, it's very simple. Of course, also, other classifiers could be non-binary. That's not, if that's just an accident of this example. You could have like a fruit classifier that has many different possible output categories. Okay, to set up sort of a little bit of machinery here to get the formal semantics going, we're going to assume that we can represent meanings for predicates. So a lot of expressions in natural language, such as nouns, verbs, and adjectives, can be modeled semantically as predicates. So the meaning of a predicate is going to have classifier parameters, possibly empty record. It's going to have a background meaning. So that's a type representing basically the assumptions about the context of the utterance, often referred to as presuppositions in linguistics. It's going to have an interpretation function for contextually interpreting the meaning of something in context, and the classification function. So just a little bit of machinery here. We want to be able to look up the meaning of a predicate for a p-type. So we have a p-type, and it has a predicate, and that predicate is associated with the meaning entry. So this, just ignore the definition and look at this. So we have this predicate of this p-type, that object 45 is to the right. And that's just saying, well, the predicate there is actually that it's just that this predicate right with that takes an individual, and then we can look at the meaning, predicate meaning for that predicate. Take the right with the one argument, who's an individual, and that's going to be this. For example, let's say now for the game we were imagining that we have parameters here with these specific numbers, background, as we saw before. These are the constraints on the situations where you can say right. The interpretation function is something that takes a situation of this type, where you are looking at some object, and the output is a p-type claiming that that object, foo, r.foo, is to the right. Okay, so it basically, the interpretation says, if you're looking at a situation where you're looking at this object foo and there's a sense reading, then what's being claimed here is that that object is to the right. The classification function, on the other hand, takes the same kind of situation, but gives output depending on the output of the classifier. So you're going to use that to actually classify the situation that you're looking at as whether it's to the right or not. And we used, again, these double brackets to just represent the interpretation function. So if you have the meaning of right here is just the interpretation function that you get if you look up the predicate right. Finally, we define the classifier related to, so we want to be able to take a p-type, like saying that something is to the right, and look up the classifier that's involved in that. So that's going to look up first the meaning related to the predicate involved in the p-type, and then look up the classifier. So if we have this p-type again, that this object is to the right, well, the relevant classifier there is going to be this function. It's taking something again of this type and giving a result depending on the output of the classifier. Okay, here is the sort of core thing here, core definition of the paper. So if you look at sort of the vanilla TTR, which is in Robin's book, if you're looking at the p-type, so what is of a p-type? What kinds of things are sort of proofs or of different p-types? It's defined as a set membership. So it's assumed here that, so it's you could say it's extensional in a way, but not in the same way as traditional formal semantics, because it's saying that for every p-type reflecting a proposition or the meaning of a claim or assertion, there is a set of proofs of that, or situations that prove that that thing is true. But what we want to do now is actually add to this that it's not always the case that you have already classified things as being of the p-type. You want to be able to classify new situations as being of the p-type. So then we say, well, if you have a p-type T and you want to check if a situation is of that type, then look up the classifier corresponding to that type, apply it to that situation. And then if you get back the type, you can then, then the situation is of that type. So you can make new judgments using this classifier function. You can also have these keep around this witness cache of previous situations that you judged. But this puts the classifiers at the core of TTR and at the core of the formal semantics. I realize that this might be a bit abstract now. So let's look at a concrete example how it actually works in this game setting. So assume that our agent A places an object on the surface and says that one's to the right, or just right. So here's the object. Agent B watches, getting a position sense reading, 0.9, 0.1, so 0.9, 0.1. And this is now B's take on the situation. So this is the sensory reading, position sensor, and this is the object. And now B wants to interpret the utterance. B said that one's to the right. And that refers to this object 45. So you want to interpret this in context. And since this meaning of right is a function that you can apply to situations, we're going to apply it to this situation. And it turns out that the output of that is this p-type claiming that this particular object is to the right. So when you say in this context, when A says right, or that's to the right, that means this object is to the right, because that's the one you're looking at. Then you can sort of do a derivation here. Here's our big meaning entry. The meaning of right is, basically this function here. reprised here, and we just put in bg here is, of course, this function. So that's what it means. And so we take that function, we apply it to this S1 that we had here, and that's going to work because the value of S sensor reading is in fact a real vector, and this object 45 is in fact an individual, so that's fine. This is of that type, this is of that type, and then the output is going to be whatever right, the predicate right, predicated of whatever is the value of foo, which is object 45. So that's what we want. Okay, we now interpret it in context. Good. But the actual more interesting thing is the classification. So now we figured out what A meant. Now we want to see if what A said is true according to the way B sees the world.
Can I intervene with one question from Tufik?
Yeah. Yes.
What is the difference between a type and a predicate?
Right. Good. So a predicate is something like right. But a type here, a p-type, is that a certain object is to the right. So it's something, you could think of it as being true or false, where it's a type of a situation. So just right in itself, that predicate doesn't express something that you would think of as being true or false, or So basically, predicates are not types themselves, but you can form types from predicates and arguments. So those are called p-types. So the idea here is that those are types of situations. Like if I say, the glass is on the table, that's a type of situation, and then many different situations can be of that type where a glass is on the table.
Can the questioner just elaborate a little bit on the question? Go ahead.
Well, okay. Thank you for the answer. I would like just to, as you know, there are a lot of definition for predicate, and we can say that the predicate is a component of a phrase that brings together a lot of objects that share the same properties. For example, red between brackets, X may be tomato, maybe meat, and we can look at predicate as a type as well. And I have a confusion to make a difference between predicate and type in your context. Thank you.
Yeah, I understand what you mean. So you could say that right is the type of all things that are to the right. But that's not, it's just not the way we do it here. We simply use predicates to construct types instead. So here we think of these p-types as types of situations. So you can say that this situation is of the type where this object is to the right, rather than saying this object is of the type right. So
okay, I see what do you mean by predicate. Thank you.
Good, thank you. Good question. Right, so what happens in classification then? Again, this looks more complicated than it is, I think. So now we want to see if the situation that we have here, S1, is of the type that's expressed by this claim. So A claimed that one's to the right. That meant in this context that object 45 was to the right, so it's this p-type. Now we want to see whether this particular situation is in fact of that type where object 45 is to the right. So we want to see if this claim is true, as it were. Whether S1 provides evidence that object 45 is to the right is another way of putting it. So we said that for a p-type, something is of the type if you take this classifier that you can extract from the p-type and apply it to that situation, and you get the type back. So now we have this particular type, right, object 45, and we know that a situation is of that type if we can take this classifier, this thing we had saw before, apply it to that situation and get this type back. So let's do that. All right, now I got into this. Just a second. I hate this. once you get into this mode where the cursor starts moving up and down again instead, you have to. Yeah, no, we're not back. Okay, I'll just go into that mode. Sorry for the extra stuff around the picture. Right, so let's check that. So now we take this function, which was the classifier function related to right, and that's this thing. So it takes something of this kind of situation that we saw, and then it returns whatever you get when you take the classifier, apply it to the parameters that we had and this situation that we're looking at. And we apply this function, so that's a lambda abstraction over R, and this, we're going to basically instantiate R with this particular situation that we're looking at. And when we do that, we get this. So this is calling the left or right classifier, with the first argument being the parameters again, and the second being the situation. And that will return, according to the definition, right object 45 if you multiply this number with, or this vector with this vector, and it exceeds this threshold, and in this case it does, so you get that result. So S1 turned out to provide evidence that object 45 is to the right. So here we see how this propositions as types of proofs works. So the situation S1 is a proof or evidence of the p-type right object 45, which was expressed by uttering right in this situation. So this is what happens in the dialogue. Right. Okay. Now it's a bit unfortunate. I realized that this right can also be taken to mean many other things. It's ambiguous, but here it means that one object is to the right. That's the basic. That's like the core stuff here. That's what we build all the other things on top of. And I now realize I have like much less time than I had hoped. But so I will simply go through basically what I take to be the most important things for the rest. So one thing is that this is very, on or off, like it's true or false, or it's of the type or not of the type. What you really want is to model vague concepts, because most or all concepts in natural language are vague. So I've done work together with Raquel Fernandez, where we formulate a Bayesian noisy threshold classifier for vague concepts in TTR. And it's also context sensitive, because you need that with a lot of concepts, like tall for a skyscraper, for a human, etc. So in this case, instead of a binary judgment, the classifier returns a probability distribution over p-types. And to do this, we have a probabilistic version of TTR, prob-TTR. And there's a paper about that. We're actually still working on improving and developing that further. And Robin just posted an implementation the other day. I haven't had time to look at it yet. Yeah, so this is how things look there. Basically, you have a noisy probabilistic threshold. But let's not go into details, but you get probabilities instead of categorical judgments. Another thing that happened was that some students built, actually, this is a very abstract thing still with this game. They actually built on top of the TTR implementation that we have, that Robin did, built and using these ideas presented here, implemented there to classify actual pictures and like test whether something holds true of that or not. And you can do that in different ways. So that's Ronja Utterscher and Arild Mattsson who did that work. And then you have like, you have an actual image, JPEG, and you have like a frame, and you can then classify that as being of a type. So it works in sort of more real life cases as well. So yeah, so one thing, you want to generalize this, of course, to probabilistic classification. We want, of course, to be able to parse into TTR with perceptual meanings, like take natural language and parse it into these abstract representations. That's also related to compositionality. We want to remove this limitation of talking about the here and now that was inherent here, and there's some work towards that. And then there are plenty of sort of shared tasks about visual question answering, visual dialogue and so on going around now, and people are only using like deep neural networks, and we would like to see if this kind of hybrid approach could help. Another thing is, of course, that classification is not just perception. Yeah.
Just to tell you, don't worry too much about time because you've been taking questions as you go along. So
yeah,
that extends
okay.
your time.
Okay, thank you. Another thing that we haven't really gone into yet is the fact that classification isn't just passive perception, but also includes action, like you might want to lift something and twist it around. So that makes things a bit more complicated. Okay, that was the basic idea about classification, how you put these classifiers into formal semantics and what role they play. Now, what about coordination and learning? So we've been working with this idea of semantic coordination for a while, and that, of course, takes its cue from work in other fields. So in psycholinguistics, for example, people have been working on alignment, showing that agents negotiate domain-specific sort of micro-languages for the purposes of discussing whatever particular domain they have at hand. And this is often, in everyday language use, not very salient to us because we often talk about things that we've talked about before, and then we already know more or less how to talk about it. But when we talk about something we haven't talked about before, or we talk to someone who we haven't talked to before about the thing, then you actually are doing this kind of negotiation and coordination. So semantic coordination is the process of interactively coordinating on the meanings of linguistic expressions. Sorry, jumped back there. So basically, in dialogue, you have two kinds of coordination going on. One is that you're coordinating on information, like you're exchanging information. What's true? What are the relevant questions? And you're making sure that you're being understood and so on. But the other kind of coordination that's going on is coordinating on the language, how to talk, which enables the information coordination. And this includes semantic coordination. And so, as I mentioned, semantic coordination can occur as just a side effect of just talking about the sort of object, the situation that you're in, not talking about language. Like you're just acknowledging, clarifying if you don't understand, you're repairing each other's utterance and correcting them. And you can even learn a new language by just observing someone else and like silently coordinating. So, I guess they mean this when they say that. So I'm just going to adapt to that, more or less consciously, of course. But there are also dialogue strategies whose primary purpose is to aid semantic coordination. And those are particularly visible, of course, in first language acquisition, also in second language acquisition, although we looked less at that. But it's also available, for example, in online discussion forums. So Jenny Myrendal, a former PhD student, wrote her thesis looking at semantic coordination in online discussion forums, because you have people who don't know each other discussing more or less controversial topics, and they often get into talking about what words mean. Very interesting stuff. Not directly, well, okay, yes. So let's look first at first language acquisition example. So this is from work by Eve Clark. So she identified lots of different strategies that children have to sort of coordinate and learn meanings. So here you have a child, D, putting, so I don't remember now exactly how these age codes work. Anyway, ignore that. So D, child, put his shoes on and points at some ants to the floor and says, ant, ant. And the father says, indicating a small beetle nearby, and that's a bug. D says, bug. Okay, so just sort of pointing to something and saying what it is, and then often as a signal of uptake of that, the child repeats the word. It can also be a kind of repair or sort of cooperative repair. So Abe says, I'm trying to tip this over. Can you tip it over? Can you tip it over? Mother says, okay, I'll turn it over for you. So sort of subtly introducing the more correct word turn rather than tip. There can also be clarification requests like, Mommy, where my plate? Oh, you mean your saucer. again, sort of subtly, without saying you're wrong, you know, but just sort of subtly introducing the correct word. So you know, from one perspective, what's happening is that you're getting the right word for a given meaning, but it also means adjusting the meaning of the words, or idea of the meaning of the words. So learning meaning. You can also do more, you know, confrontational strategy, like Naomi says, birdie, birdie, not a birdie, a seal. So again, you would expect Naomi to learn something from that about the meaning of bird and seal. And they can even be just bare corrections like mittens, gloves. So we've done some work on this kind of acquisition in TTR a few years ago now. But how would that work in our language game? So we had this meaning of right that looked like this. You have these parameters of the classifier here for being to the right. That's part of the meaning of right. Let's now continue with the game. Now, this time, A puts a new object here, okay, and says right. This one's to the right as well. So this gives a new sensor reading. These are the new coordinates. It's also a new object. And as before, B computes the contextual interpretation. It means when A says that one's to the right, in this context, it's now the claim that object 46 is to the right. Next, B wants to see if this correctly describes her take on the situation. So is the situation 2 of the type that you get if you interpret the utterance in context? So is it of this type? Is it evidence that object 46 is to the right? And if you go through the whole derivation as we did before, it turns out no, this time it's actually to the left. So the left to right classifier now returned that object 46 is to the left, and we can see that because it's to the left of this dividing line between left and right that B takes to be, you know, the meaning of left and right. So A's utterance doesn't correctly describe B's take on the situation, but B is learning and trusts A to know better. So B will learn from this by updating the weights used by the classifier Perceptron, and then you can just use, so there is a standard Perceptron training rule, and any kind of classifier or classification method or deep neural network has different ways of updating the network based on observations. So basically you compute like a vector corresponding to taking into account the target output, the actual output, and the input. So this is what you perceived, this is what the teacher said, this is what you thought. And then you compute an update based on that. And I'm not going through the details of that, but it's going to end up updating your weight vector in the meaning of right. So now that's how you see that something changed as a result of learning here. And that, if you make it into a picture, means that you move this dividing line a bit to the left, and now this object is actually to the right of that line. So now B said, aha, indicating that B learned something. Okay, so this is asymmetric, of course. B is learning from A. But when humans interact, when adult humans interact especially, they mutually adapt to each other's language use on multiple levels, and this is evidenced by the work I cited before from psycholinguistics. In fact, it's quite easy to alter this game to illustrate coordination directly. You just make A and B switch roles after each round, and that means, you know, well, in the kind of asymmetric version we were looking at, B will ideally end up with the exact same meaning for right that A had at the beginning. But if they are learning from each other, then they are probably going to end up with a meaning for left and right that's different from what any of them had to begin with. Let's actually skip that. Yeah, but not so. one thing to note is that in this game, the left or right game, coordinating on the meaning of left and right is sort of the main goal of the game. It's like a learning game. But of course, it could also occur as a side effect of doing something else. Maybe you have a game where you need to give me the left cup, give me the right cup. Oh no, that's not the left cup. You know, so you could like a side effect of identifying objects, you can learn meanings as well. It doesn't have to be the goal of the dialogue to learn meanings. It can happen anyway. Right. So I want to say a few words about this work that Jenny did for her thesis and that we continue to work on together after that. Basically, the idea is to sketch a general account of dialogue acts for semantic coordination, like these strategies that people have when they discuss meanings of words. So Jenny in her thesis found a number of strategies. There's a list later, and we tried to sort of put that taxonomy together with the one by Eve Clark and colleagues. So that's in that 2017 paper, because presumably there's like a universal inventory of strategies for learning. Well, universal is a big word, but you know, yeah, an inventory of strategies for negotiating and learning meanings. And some of them are employed in first language learning, some are employed in semantic coordination among adults, and some in both. And we also want to connect those dialogue acts, or these different ways of doing negotiating meanings, with updates to the meaning representations, like we did now with the classifier. Yeah, so what Jenny observed was that people engage in these word meaning negotiations. There's a trigger word that they start discussing, and then you know, they can either be cooperative and end up, okay, that's now I understand what you meant, or they can continue to disagree because there's some kind of something at stake that you don't want to lose. Like defining the words is part of winning the argument, and then those discussions can go on forever. So the kind of taxonomy that Jenny was looking at was, okay, so you have something called expecification, or just explication, where you basically provide some kind of definition. Or you can give examples, exemplification, like providing examples. And actually what we saw in the left or right game was, in a way, providing examples. This is an example of being to the right. This is an example of not being to the right. You can also contrast the word with another word. This is not to the right, it's to the left. You can just oppose, like, no, you're wrong, that's not to the right. You can ask for clarification, and you can endorse word. You can just use a certain word to show that you're endorsing using it, and that's, you know, often done in sort of political context, like political arguments. You use a word that has certain connotations to signal yourself. It's part of winning the argument. And Bill Noble is working on continuing to develop this. He's a PhD student of mine now, developing this kind of taxonomy further. I'm going to skip a little bit here again. So what we want to do with respect to coordination is to work out then a general and reliable taxonomy or annotation schemas for semantic coordination strategies in general, and relate that to updates to meanings in a way that works both for high-level inferential meaning, so that can include giving explicit definitions, but also for low-level referential, including perceptual meaning, like the kind of thing we saw in the left to right. We also want to be able to automatically detect semantic coordination strategies in dialogue, and also, of course, enable artificial dialogue agents to participate in semantic coordination in dialogue. So yeah, that's where I can mention Tokimatic, I guess. So, you know, a well-known problem with dialogue systems is that they only know the language they've been programmed or trained. They can't learn new language by talking to people, and that's what we do all the time. So that would certainly be a big help if like, say, you have a household robot somewhere in the maybe not too distant future that you want to tell how to do different things, and you have to explain to it and make it understand what you mean when you talk about, like, cleaning different parts of your home or whatever. So Another thing is that, of course, word meanings don't exist in isolation. They hang together in larger sort of structures or semantic systems that encode a perspective on a situation and an activity. And that is sort of, now we just looked at these words in isolation. So changing the meaning of one word is going to change the meaning of another word. In the left or right game, it's obvious. Like if you change the meaning of left, right, you're also changing the meaning of left. So that needs to be taken into account. And we didn't say much about that yet. Another thing is, of course, how do agents figure out, like if you say something and the other person indicates more or less explicitly that there's something wrong with your utterance, that's not how you should use that word. You don't have the right idea. Right, that's actually another problem than the one listed here. But okay, so one thing is like, how do I figure out what was wrong with my my meaning, sort of? A part of that is to figure out what classifier you train for a given word. How do I even know that right is about position rather than color? So that's, and there are various clues like how children do that. One thing is you can know, like have ontological knowledge. You know what kind of thing something is. Like, yeah, you can even be told that red is a color. But you can also learn this from interaction more subtly. And like there might also be biases, like infants have a shape bias, so they are biased to take words to refer to shapes rather than colors initially. Yes.
Could I suggest maybe, as I said, you had more time, but to make this, to use this remaining time more economically, leave aside the details, the papers can be read, and give the generalities that might be useful in the 20 minutes of discussion that we still have left.
Yes. Let me then skip to compositionality. That's my last point, and try to go over that. Yeah, so here's a quote from you. I just want to emphasize, I have these quotes in my talks, not just when I give talks here. So, you know, categorical representations cannot be interpreted as meaning anything. It's true that they pick out the class of objects they name, but names don't have all the systematic properties of symbols in simple systems. They're just an inert taxonomy. For systematicity, it must be possible to combine and recombine them willfully into propositions that can be semantically interpreted. Yeah, so if we have something that doesn't just have one word like right, if we have several words that have perceptual meanings, how then do you put them together? And let's just take this left and right game and add like upper and lower. So now we have, okay, here's the meaning of right, here's the meaning of upper. It calls an upper or lower classifier instead. So if someone says upper right, it's to the upper right. Well, then we can just combine the meanings of upper and right using this merge operator. So it's just going to basically, you know, you need to be classified as being, you need to merge, you need to classify both as being upper and to the right. So that's a very simple kind of compositionality. It's basically just conjunction, like upper right means upper and right, like this. Okay, so if it's upper and right, it's here. That's not very problematic. However, there are other more interesting cases. Like what if you say it's to the far right, not in the political sense, in the position sense here. Geometric sense. That doesn't mean far and right? It means far somehow modifies right, and we can model that here by, and I'm definitely not going into the details here, but basically the meaning of far is a function from a meaning to a meaning, and what it does is to change the threshold of. So if you take right being this, and then you take far right to provide a new threshold, it increases the threshold, thus pushing the line here to the right. So if right means this, then far right is going to modify that classifier into a new classifier looking like this. So that kind of compositionality is more challenging, right? And then that can be presumably become quite complex when you combine different modifiers like that. So to cover compositionality, you need to not only cover this kind of simple intersective compositionality, like upper right meaning upper and right, but also this what I call non-intersective compositionality, where you have more complex relations between the meanings. You also want to be able to account for learning perception meanings, vagueness, and if you're into computational stuff and want to build robots, you want to be able to use the best classifiers and make it work with them. Yeah, so skipping over a few slides here. So far, we haven't seen any account of compositionality for perceptual meanings models as classifiers that satisfy all the desiderata, and even the one that I showed now is not great because, well, it fulfills everything except you can't really use it with these deep learning classifiers because there you have you can't like manipulate parameters of those classifiers in a way that you understand, because by definition the weights in those networks it's very hard to figure out what they do. So it's hard to know how to modify them. We have some ideas toward the solution there, but we haven't published that yet. You can also think about how compositionality and learning interact, because if no, that's not to the far right. Well, is that because it's not, I have the wrong meaning of right or the wrong meaning of far? Hard to know. And how can you use definitions in learning compositional meanings? Like how can you learn, rather like this, if you give a definition, that can be used to learn a new meaning, but then you need to understand that definition. That definition is going to be a complex expression that you need to interpret compositionally. To conclude, we described work on formal semantics for perceptual meanings, meaning coordination and compositionality for perceptual meanings. And hopefully the message came through that TTR is well suited to modeling agents that coordinate on informational language, including perceptual meaning, and also that there is still a lot of work to be done. Thank you for listening.
Thank you very much.